All right, here we're looking at section 1.4, and our essential question is how can you determine the number of solutions of a linear system? So a system of equations is just more than one equation kind of on the same plane, and we're going to look at just a minute what this kind of looks like visually. But first let's look at our learning targets. Our first one is we're going to visualize solutions of systems of linear equations in 3 variables. This is kind of the big difference here is we're looking at 3 variables. We've looked at 2 often, but now we're going to look at 3. It's honestly fairly similar to how we've done 2. The second one we're going to do is actually solve those systems in 3 variables, and then we're going to look at that system in some real life problems. Okay, so first we want to kind of look at our steps, and we're going to walk through these over and over. So if you don't write these down exactly, that's just fine. So our first step is to rewrite the system that's in 3 variables as a system in 2 variables. We're going to either use substitution or elimination, whichever one works best. If you totally remember substitution and that's all you remember, great, use that one. Then step 2, we're going to solve the new linear system for both variables. And then 3, we're going to substitute those variables that we just found into the original equation. And just like when we were solving those simple 2 variable equations, if at any point I get a false equation, such as this one, 0 equals 1, right? I know that's not true. I know that I have no solutions. So if I get this at any step, that's a no solution. So if I obtain an identity, such as 0 equals 0 or 12 equals 12, something like that, I know that I have infinitely many solutions. So you just want to keep that in mind. So first let's look at what they look like. So here we see we have 3 different planes, and that's really what we're looking at with these 3 different variables, is these 3 planes, and they're shown in 3 different colors here. So it's possible for me to have one solution, and that would be this dot right there, this point. That's the only place where all 3 of my planes meet. It's possible for me to have infinitely many solutions, right? That's here, where you can see that these planes will continue to meet forever and ever in both directions, right? Going up and down. So they could also be the same plane. That would be another way to visualize this. There's another possibility that I have no solution. So in all 3 of these examples, there's no place where I have all 3 planes that touch. So that's how we can visualize it. So now let's look at our second learning target was solving these systems, right? So here I see I have my 3 equations and I have my 3 variables. The first thing I always want to do is line them up. So I've got x, y, z equals my constant. X, Y, Z equals my constant. X, Y, Z equals my constant. That will just make our lives a lot easier if we can always line them up this way. Okay, so now let's try and figure this out. So here's my solution. Here's what I do first, right? Step 1 was to look at this in 2 variables. Okay, let's go to right there. So I see I take 2 of my equations. It doesn't matter which 2 of those equations I take. So for this one, I took my 3rd equation and my 1st equation, right? So here's my 3rd equation and my 1st one. It doesn't matter which ones you pick. And I multiplied that 3rd equation times 2. Okay, so that's how I ended up with 12x minus 2y plus 8z equals negative 6. That's all I did was I took this 3rd equation, this 6x minus y plus 4z equals negative 3, and multiplied everything times 2. And I did that because I see right up here in this first equation I have a positive 2y, and that's an easy way for me to get a negative 2y right here, which will get rid of one of my variables, and that's the goal. Okay, so that's why I did that. So I multiplied that entire 3rd equation by 2. So now I'm going to add my 2 equations. Okay, so when I add 4x plus 12x, I get 16x. My positive 2y plus a negative 2y gives me 0, so that's gone. And now I have 3z plus 8z gives me 11z. And then I have 12 minus 6 is 6. Okay, so now I have this is going to be my new equation, right? We're going to call this new equation 1. Or I'm going to put a red star by it. So now I'm going to take 2 more of my original equations. So here I used equation 2 and equation 3. And I'm still trying to get rid of y. And I'm trying to get rid of y because that's what I got rid of in this first one. Okay, so I take my 3rd equation, that same equation I used before, my original 3rd equation, right, this one right here, except I'm going to multiply everything times a negative 3. And that will help me also eliminate my y values. Okay, so once I do that, I end up with a negative 18x plus 3y minus 12z equals 9. So now that I can do that, I'm going to add these 2 equations together. So I have 2x minus 18x, which gives me a negative 16x. My y's, again, go away. And then I can deal with my z's. So I've got 5 minus 12 gives me a negative 7. Negative 7 plus 9 gives me 2. So now here's my new equation number 2. my second one that I'm going to use. So now that I have these two with my red stars, I'm going to go ahead and solve these as just a normal system, right, of two equations with two variables. And this I've done before. If we need some refreshers, come see me and we'll definitely go over solving some systems. And I'll try and make it as easy as I can. So really I just line up my two new equations, right? So I've got 16x plus 11z equals 6. And then I've got negative 16x minus 7z equals 2. Well, this one's handy, so I see I automatically can get rid of my x's by adding these equations together because one's positive and one's negative and they're the same value. So I've got 16x minus 16x, which gives me 0. 11z minus 7z gives me 4z, and then 6 plus 2 is 8. So now I can just solve this simplified, right? Because I know that if I just divide both sides by 4, I end up with z equals 2. So now I can plug this z back into either one of these two equations and find out what x equals. Okay, so it doesn't matter which one I pick. I would probably go for this top one because they're all positives and it's just easier for my brain to handle that. But it doesn't matter which one I plug this z into because I'm still going to be solving for that x. Well, so now I've solved for x and I've solved for z. So now I can take both of those values back into one of my original equations. And again, it doesn't matter which equation. Here they just picked the third equation that we used and plugged both my x and my z in where I found them, and I solved for my y. So now I have all three of my variables. I have an x, I have a y, and a z, and I can double check that. And I can also write this as an ordered triple, right? So I've seen ordered pairs a lot when we're graphing things, but I can write this as an ordered triple, which will also make sense. So now let's look at example 2. This is example number 2 in your book. So again, solve the system. So again, I have my three equations with my three variables written out in the right way. So I see I have x, y, z equals my constant, x, y, z equals my constant, x, y, z equals my constant. So as long as they're all written the same way, that's going to make things a little bit easier. So I want to follow the same steps that I just did in that last one. Okay, so my first step is I rewrite as two variables. So here I took equation 1 and equation 2, and I'm going to multiply equation 1 times a negative 5, because then I can get rid of my x's, right? So once I multiply the entire equation by negative 5, and I add the two together, I end up with 0 equals negative 7. Man, this looks like that's not true, right? 0 does not equal negative 7. So because I have that false equation, I don't have to go any further. I can say that this has no solutions, right? And I could do that just because at any point in my equation I ended up with a false equation. It tells me I have no solutions. So now this is example number 3. Let's look at this one. So I've got x, y, z equals constant, x, y, z constant, x, y, z constant. Great. So now let's start and go from there. Okay. So I'm going to look at my, again, two variables. And for me, I would start with these two at the top because I see I have a positive z here and I have a negative z here. Well, I can automatically get rid of my z's without having to multiply by anything. So that's what we're going to do. So now I can add those equations. So I have 2x. I have a negative 2y, I have negative 6 because my z's go away. So that's my new equation. Okay, so I have to do that again. Well, again, I'm going to use, for the second one, these two, because again, I have a negative z and a positive z, so my z's will still go away when I add these two equations together. So that'll be a little more simple. So again, I can add my x's and my y's and end up with a constant. So those are my two new equations. So now I solve for both of those variables. So I'm going to be using these two equations right here. My 2x minus 2y equals negative 6, 6x minus 6y equals negative 18. So I set those up and I try and solve them. Well, here I see I end up, once I add them, negative 6x plus 6x gives me 0, 6y minus 6y gives me 0, 18 minus 18 gives me 0. So now I end up with 0 equals 0. So I know here that I have infinitely many solutions. So remember back when I said I end up with a true identity of 0 equals 0 or 18 equals 18, something like that. I know I have infinitely many solutions for this one. Okay, so here's your first monitoring progress. The big thing I want you to look at in these is definitely try and solve one or two of them, but try and figure out which ones would you solve first. What two equations would you use first to try and get rid of your variables? So now here's our last example. This is example number 4. Okay, this is our kind of a real world problem. So an amphitheater charges $75 for each seat in Section A, $55 for each seat in Section B, and $30 for each lawn seat. There are 3 times as many seats in Section B as in Section A. The revenue from selling all 23,000 seats is $870,000. How many seats are in each section of the amphitheater? So this is going to take us several steps, but again, it's not that bad. We just have to lay out what we know and what we're trying to find. So we want to look at things in pieces here. Okay, so I'm going to write out my model, and this is just taking the words from the sentences and actually putting them in math. So I was told that the number of seats in B, and we're going to call B Y, is, whenever you see the word is in word problems, that's where your equals goes. 3 times the number of seats in Section A. In Section A, we're going to give the letter X. So there's going to be one of my equations. Okay. The number of seats in Section A, which is X, plus the number of seats in Section B, which is Y, plus the number of lawn seats, is the total number of seats. And now here's where the money comes into play. Okay. So $75 times the number in X, plus 55 times the number in Y, plus 30 times the lawn equals my total revenue. So now that I have this kind of verbal model written out, I'm going to replace the things that I have numbers for. So I'm going to write my system. So you'll see in my first equation I just have Y equals 3X. My second equation, and I don't know how many number of seats there are in each of these, so that's why I still have X plus Y plus Z equals 23,000. And then my third equation, 75X plus 55Y plus 30Z equals 870,000. So now that I have them all written out, I still have my system of equations, I can go ahead and solve them. So one thing I'm going to do a little bit differently is I've already got one solved completely, right? So I know Y equals 3X. So I might as well go ahead and plug that into both of my equations, right? Because that'll make things a little bit easier. So now I can simplify. So I'm going to end up with 4x plus z equals 23,000. Because all I did here was I took this 3x and I plugged it in where I saw a y right there, because I have a y right there. So I can do that. Well, I might as well do that down here as well, since I have a y right there. Plug that 3x in and simplify there. So now again I see I have my 2 equations, that I have 2 variables that I can then set equal and solve from there. So now I just have my system of 2 equations, and what I want to do is I can either use substitution or elimination. We generally, elimination can be a lot cleaner to use, so we're going to do that. So I see I'm going to deal with my z's. I want to get rid of z's first because they're smaller numbers. So to get rid of these z's, I'm going to multiply this entire equation by a negative 30. And I pick a negative 30 because this is a positive 30. And to get rid of that positive 30, this z would have to be a negative 30. So that's where we do this. So I end up with a negative 120x minus 30z equals a negative 690,000. So now that I can do that, I add both of my equations together. So these go away, and I end up with 120x equals 180,000. Then I divide both sides by 120, and I end up with x equals 1,500. So I know that there are 1,500 seats in Section A. So from there, I can just go back and solve and substitute back into equation 1, right? Because here I just had x and y. Well, if I find out what x is, just plug that in and solve for y. So that's where I end up with y equals 4,500. Now I have x and y, and I can pick any of my original equations and solve for z. So now I see I have all 3 of my variables and all 3 of my letters that I figured out. So now here's something I want you to think of. It's a kind of similar to this last one, is how can I figure out the different seats? What do I have to tweak in my equations? Okay. So now let's look back at our learning targets. First of all, we visualized solutions of systems of equations in 3 variables, and that's where we looked at those 3 different colors of planes and how they intersected. Then second, we solved those systems of equations in 3 variables algebraically. We did that several times. We looked at one where there was an actual solution, we looked at one where there was no solutions, and we looked at one where there was infinite solutions. So look back at those. And then we solved that real life problem. Okay? So now that we've gone through these learning targets, I want you to go ahead and practice and work on that homework for 1.4.